Black holes may be well known for their gluttonous tendencies, but they're not the only dead stars capable of slurping down passing objects. For years, evidence has been mounting that white dwarf stars also have a penchant for snacking, and on their own planets, no less. Now, for the first time, astronomers have caught such a Cronian meal in action, betrayed by the flare of X-ray light as material from the planet falls down onto the stellar core. We have finally seen material actually entering the star's atmosphere, says astrophysicist Tim Cunningham of the University of Warwick in the UK. It is the first time we've been able to derive an accretion rate that doesn't depend on detailed models of the white dwarf atmosphere. White dwarfs, just like neutron stars and black holes, are the collapsed cores of stars that reached the end of their main sequence lifespans when they ran out of fuel for nuclear fusion. What differentiates them is the mass. White dwarfs are the cores of precursor stars up to 8 times the mass of the Sun. Neutron stars and black holes are from more massive stars. During the end of its life, a dying star ejects most of its outer material. Nevertheless, exoplanets have been spotted orbiting white dwarfs. And in recent years, astronomers have spotted signs that white dwarfs may have been accreting or forming exoplanets too. In the atmospheres of these dead stars, we've seen hints of really surprising elements such as iron, calcium, and magnesium. These are heavy enough that they should have disappeared, sinking into the dense interior of the white dwarf. Such white dwarfs are known as polluted, and the study of their devoured exoplanets, based on spectroscopic analysis of the star's light, is known as necroplanetology. Previously, measurements of accretion rates have used spectroscopy and have been dependent on white dwarf models, Cunningham explains. These are numerical models that calculate how quickly an element sinks out of the atmosphere into the star, and that tells you how much is falling into the atmosphere as an accretion rate. You can then work backwards and work out how much of an element was in the parent body, whether a planet, moon, or asteroid. This new work is different. Rather than detecting elements in the white dwarf's atmosphere, the team detected high-energy light emitted as material from the ruptured exoplanet collided with the star. When a compact object such as a white dwarf or a black hole accretes another object, it's not a clean event. First, the orbiting body is tidally disrupted, that is, the gravitational stresses as it grows too close to the dead star tear the object apart. Then, this orbiting stream of material, in this case, exoplanet guts, spools into the star from a disk for an extended accretion event. When material from the dead exoplanet slams into the star at a high enough rate, it generates a plasma shock heated to temperatures between 100,000 and 1 million Kelvin, around 100,000 to 1 million degrees Celsius, or 180,000 to 1.8 million degrees Fahrenheit. This then settles onto the surface of the white dwarf and cools, emitting X-rays as it does so. Cunningham and his team used the Chandra X-ray Observatory, which is used to detect X-rays from accreting black holes and neutron stars, to study a polluted white dwarf named G29-38, located 57 light-years away. It's thought to be relatively young, having collapsed just 600 million years ago. Previous studies also suggest the white dwarf is surrounded by a debris disk and has heavy elements in its atmosphere. With Chandra, the researchers were able to isolate G29-38 from other X-ray sources in the sky. Sure enough, they found the X-ray signal generated by accretion. The result finally confirms that white dwarfs are indeed quite violent objects, and gives astronomers a new tool for probing these fascinating interactions. What's really exciting about this result is that we're working at a different wavelength, X-rays, and that allows us to probe a completely different type of physics, Cunningham says. This detection provides the first direct evidence that white dwarfs are currently accreting the remnants of old planetary systems. Probing accretion in this way provides a new technique by which we can study these systems, offering a glimpse into the likely fate of the thousands of known exoplanetary systems, including our own solar system.